Good morning, everyone. Today I will be presenting Winds of the West. This is going to be an analysis of the topography and the inversion slash marine layer combo that we get on California and Baja, Oregon, really any west coast of a northern hemisphere continent. And let's jump right into it. So this slide's all about what maintains the marine layer, also what creates it. And you've probably heard of high pressure off the west coast of California. This is the semi-permanent high. Um, and what high pressure does is it's sinking air. Sinking air does two things. It does warm as it descends, and it keeps the air below it kind of in one place. So when the air interacts with the water, you get marine air, and then when you have warm air above it, that's pushing down on it, subsiding on it. It doesn't really have anywhere to go, and voila, you have a marine layer. Next slide. What is an inversion? So above the marine layer, believe it or not, the temperature actually increases. This has to do with the subsiding air we just talked about. And another way to think about this is if you have warm air over cold air from a buoyancy perspective, that cold air, the marine air, is not going to rise through the warm air. And here is a plot from Windy. And basically you click on the point you want, right click on the point you want, and go to a sounding forecast. And this red line represents temperature. So at the surface, it was approximately 20 degrees C. And then at 1,781 feet, the model says it's 28 degrees C. So this right here is the inversion. This blue line's dew point. Sometimes it's nice to compare the dew point and the temperature, and where they overline, you're more likely to get clouds. But here, so we found the inversion. Next slide. Okay, now we're going to get into the fun stuff. So I'm not going to talk too much about high pressure here, low pressure here, big synoptic situations that create California wind. So let's just imagine, as scary as that word may sound, that there's high pressure over here, low pressure over here. Maybe another way you want to think about it is the coast is cool, inland's hot. A lot of these examples that we're going over are for summer wind. So in that case, you do have a pressure differential setting up wind coming down the coast. I believe this exact example is for Big Sur, this topography that is. And so basically up at the top here, you see the clouds. So below the clouds is cool, above the clouds is warm. And how we're going to use the topography, why California has so many amazing setups, is that as the wind comes down the coast, it approaches mountains. So here it has a mountain, and basically that marine layer piles up against this mountain. It builds vertically, it slows down, and then what happens after this mountain? There's kind of a dip right here, right? So as this dips, this marine layer, you can kind of see it in this picture, it decreases with height and spreads out laterally. The COMET program has defined this as an expansion fan, and these expansion fans are the entire reason I'm doing this video. A lot of when people talk about the Venturi effect, Bernoulli, blah blah blah, which is technically this expansion fan right here, but it's used in an incorrect way. A lot of folks use the Venturi effect. They'd use it like right about here, where the flow looks like it becomes the most narrow, or in the gorge where it looks like it becomes the most narrow. But really, you're going to expect the fastest flow just after this pileup right here and where it spreads out. And so in this case, the pipe for the Bernoulli flow becomes right here because it's spread out this way and the height decreased this way. Okay, so air piles up, we have an expansion fan. They even go on to talk about a hydraulic jump, which you can see sometimes. Hydraulic jumps are kind of like maybe you've seen Jamie O'Brien break the creek and then ride the river waves. And so basically, when a fluid, is at a height and it goes downhill, it has maybe not so much energy, but it has so much energy that at the bottom of it, it wants to jump up vertically again, and it kind of makes another wave. So the focus here is expansion fan, hydraulic jump. We're just kind of throwing it in there. One more thing I want to say about Bernoulli is that, again, Bernoulli, you need a pipe. It needs to be closed on all sides, and that's why it can be controversial to use it in atmospheric sciences. So this whole inversion idea that we're talking about is really crucial because the mountains are a good, rigid side for this pipe that we're talking about. And on top, if you have that buoyancy from the warm that we're talking about, this cool air kind of is like it's in a pipe. Not a perfect one. Again, it's a little hand wavy, but that's the idea. Here are their descriptions of this animation from the Comet program. Comet program's really amazing. I think anybody can sign up. They have tons of not instructional videos, but educational videos on weather, geophysics, all around the world. So here we go. This is probably the most important slide out of this whole presentation. California wind. Marine layer comes up to a mountain, piles up, releases. That's called the expansion fan. You're going to expect your fastest winds around here. So here's a fun example that iKite kind of has of some, it's kind of an expansion fan example, but basically here we have a marine layer and then something's forcing up the marine layer, and after that we have these waves. See these lines here? They're defining them as gravity waves. Other people call them buoyancy waves. And again, the idea is it's like an ocean. In the ocean, there's water and then dense water on the bottom and then less dense air on top. And that difference, when there's a disruption, gravity will be the restoring force, and the waves will propagate in the ocean. In this case, you have a marine layer that's quote unquote dense, not nearly as dense as the ocean, of course. And then above it, you have that warm air, which is less dense. So in this case of the atmospheric gravity waves or the buoyancy waves, there's going to be, when there's a disturbance, the restoring force is going to be a reduced gravity. So not the full gravity, but a reduced gravity. And so in this blog that they wrote, iKite's pretty amazing, by the way. I really recommend you check them out for forecast and their blog. But in this example, they say some gravity waves were set off. They propagated down here. Waddell is where the sensor is. And these are where they believe the waves are sensed. So pretty cool example right there. You would not have these, unlikely to have these, with the lack of a marine layer or inversion. Okay, so now we made it to the fun part of the video where we will go over certain wind locations throughout Baja, SoCal, and Central Coast. And we're going to compare it to topography. So let's zoom out real quick. All right, we got a good view of the West Coast. Seattle's up here, Baja's down here. I don't know why it's not loading, but that's all right. And let's see, here's our scale, 13,000 feet. Where do we have 13,000 feet mountains? Well, we have mountains here that are approximately that. Do they affect our wind? Sure. On a sea breeze day? No, not really. So let's zoom a little bit more into the coast, try to get those out of the way. We have coastal mountains right through here that are about 3,000 to 5,000 feet. Gotta believe me. Yeah, there we go. These are crucial for Big Sur winds. And then Baja has some really big mountains. Right down here, 8,000 feet. SoCal has some enormous mountains as well, 5,000 to 8,000 feet. But really, I'm doing this big zoomed out view to show the shape of the mountains. So on the Central Coast, our mountains run northwest to southeast or something of that form. SoCal has transcendental mountains, so west to east. Baja has, again, that northwest to southeast shape to it. And let's zoom in really quick here. I think it's loaded. Let's talk about locations that do not have wind at all. So based off of what we just learned with this expansion fan idea of, a pressure differential or wind coming down this way or this way of sorts, we'd expect wind off of here, through here, through here, through here. But what happens when you come to South Orange County and below? Here's Saddleback Mountain. There's nowhere for that. Sure, the air piles up, but there's nowhere for the air to really escape. Almost through Oceanside, but not so much. And same thing for San Diego. If you're familiar with the wind community of SoCal, we always make fun of San Diego people because they get no wind. And in the winter they can get really good wind, but in the summer it's these mountains right here. There's nowhere for the air to pile up and then release to. Okay. So let's go back to our animations, or this was an animation. And basically here we go, we're on the Central Coast. This is Santa Cruz, North Coast. We're getting into Big Sur through here, and let's evaluate and analyze their topography. So just off of here, we see the wind speed increase. So if I didn't even know this area, I'd imagine that there's a mountain here and a big valley or, lack of a mountain through here. Similarly for these hotspots. So let's go up to Santa Cruz. And I already know the answer, of course, but what do you expect? So here's Año Nuevo Island. The wind pressure builds up against here, and then it kind of collapses right through here. Winds accelerate, spread out into the bay, go inland, go wherever they want. But if you know wind, Waddell and this whole North Coast region is truly world class. Another funny thing we should mention about wind is there's a little bit of a fight going on where wind does not like friction. If you probably know that wind usually increases with altitude, that's because there's less friction. But this specific example of this pipe, this expansion fan, we're using the idea that the topography kind of slows it down, but it's also going to speed it up. Yeah. And then if you probably remember from that animation or that picture on the last slide, there were some speed ups through here and here. So there's Gorda. And as you can see, we got our mountains and our lack of mountains. And yeah, that's really it. We're kind of just verifying, evaluating this theory. Okay, SoCal, here's Point Conception. Here's a bunch of islands through here that we'll look closely at the elevation of. And Leo Carrillo down here. So Point Conception again, the wind piles up, releases. All of those little increases wind speed are at the corner of the islands, right? Because the wind's going to pile up and then release, pile up and release, pile up and release, pile up and release, pile up and release. And let's see, got to zoom in here. Topography, pile up, release. Leo Carrillo, probably my favorite spot, does this as well. So the wind comes, slows down, piles up and releases. Piles up and releases. Long Beach is an interesting one, where Palos Verdes is, let's see, I think it's about 1,500 feet. So it's definitely going to have that pile up and release program to it. But another thing I've heard about Long Beach that they put in a parking lot here back in the 80s. I forgot where it is. And basically all this concrete, asphalt, whatever it was black, it was dark, it changed color. So it enhanced their sea breeze. But they also get a taste of this expansion pan idea. And again, once you come down here, you're kind of running out of wind. Huntington Beach can stay windy, but the second you get to Newport, these mountains right here, they're little, but they're enough. These mountains really kill your wind. and Orange County south, a sea breeze exists, but really, really weak. All right, let's finish with Baja. And let's see. So we're looking at Guerrero Negro, kind of in this region. So we already know that there's probably going to be some big mountains through here. And yep, what do you know? So here is some big mountains. Wind's going to pile up and release. A lot of strong wind through there. We were really zoomed in on these islands. Pile up, release, expansion fans. You know the drill. So yeah, all the way down to Abre Ojos right there. Let's see, and Abre Ojos had one as well. World-class wind spot. So wind piles up, releases. Okay, so I think that's the end of my presentation. Just a fun little catch-up, really. I guess I'll go over one more thing that's not really related, but kind of related. And I really shouldn't, but I guess I will. If you're from Ventura, you've probably seen on Santa Ana days, we get really strong Santa Anas, especially out of Oxnard, sometimes in Ventura. And then around, anywhere from 11 to 1 to 2, the wind reverses. And if you've ever wondered why those Santa Ana days are so strong, sure, inland's warm, it creates the temperature differential, blah, blah, blah. But at 11 or 12, when the wind switches at the surface and becomes west, up aloft, 1,000, 2,000, whatever many feet above, the wind is still blowing east to west all day. And basically, as that marine layer comes in, marine air comes in, and that hot air rises, that east air aloft gets rid of that wind, returns it to the ocean, so it amplifies, increases the sea breeze activity right there. Yeah, I hope you enjoyed, and that's that. Have a great day.